we can start. So our third speaker of the morning is Lucía López de Medrano from IMATE, Cuernavaca, and she's going to talk on the genus of tropical curves.
Well, thank you very much for the invitation. I hope you can hear me. My voice is not very loud. I'm going to talk about work in progress with Benoit Bertrand and Erwan Brugale. The work is a little bit more general. It's not only for curves, but for today I only have half an hour, and I think the idea of curves will give a good idea of our project. And then again, I'm going to start with a classical case. And the idea is to make like something analogous as the Cartel curves for tropical curves. What it means, if I take D, a degree, and N, a dimension, I want to ask the genus of a curve of degree D in the n-dimensional space. For example, for CP2, if I take cubics, I have two cases, the genus 1 cubic or the nodal cubic who is of genus 0. Okay? In general, if I fix D, I can ask the maximal genus of complex curve of degree D in CP2. And the bound is D minus 1, D minus 2 over 2. And in fact, is the number of lattice points in the triangle with vertices 0, 0, D0, and 0D. For example, again, for D equal to 3, the bound is equal to 1. We have only one integer point in the triangle of size length 3 h. And in general, we can ask the same question in higher dimension. This is the work on the end of the 19th century. And for example, I'm going to make an example on CP3. If I take a cubic of genus 1, we know that it's always planar. For example, if I take a cubic of genus 1 in CP3, it's contained in a plane. I'm going to make this example in tropical, that's why I have to. Now let's see the tropical picture. These two pictures are exactly the same as I have in the first slide. It's a cubic, tropical cubic of genus 1, and a tropical cubic of genus 0 in R2. Tropical curves for me will be embedded rational weighted graphs, balanced graphs. For example, this is R2. I have a line. This is a degree 1 curve. And I have 3 conics, different conics. And my definition of a tropical curve will be a rational balanced graph in Rn. And each one of these objects has a degree and a genus. Then I can make the same question. I'm going to make a picture of the definition. Rational means that each is an embedded graph in Rn. Each edge is parallel to a vector with integer coordinates. And balance means that if each edge has a weight, here the weights are omega 1, omega 2, and omega 3, and we have a primitive vector for each edge pointing away from a point P, we know that this is the balancing condition. You can think about it that in each point, if I have something that I don't know how to say, a cord or whatever that I'm pushing in direction V with force omega P, nothing happens. Everything stays. Okay, then on a generic curve in R2 look like this. Here are many things that may happen, but in the infinite edges we'll have some edges in direction minus 1, 0, and the sum of the weights is d, where d is the degree. We have some edges in direction 0, minus 1, and the sum of the weights is also d. And we have some edge in direction 1, 1, and the sum of the weights is d. This is how it looks like a tropical curve of degree d. In R2, we have a beautiful property of tropical curve, that is the duality. We have its Newton polytope, and the curve is dual to a triangulation of the Newton polytope, polygon in this case. And in more general, we have a generic tropical curve in Rn. Then we have something here, and we have rays in direction minus E1, minus E2, minus E3, minus En, and edges in direction 1, 1, 1, 1, 1. And again, the sum of the weight in each direction is the degree. What does the genus mean? The genus is, we can parameterize our tropical curve with an abstract graph, and the genus is the minimal genus of a graph that parameterizes our curve. For example, this one cannot be parameterized for a genus 0 graph, but this one we can separate this double box. We can ask again, which is the maximum of the genus of tropical curves of degree 2 to degree d in R2. And again, we have exactly the same number as in the complex case, and it's because of the duality, the number of independent cycles will be exactly at most the number of integer points in the trend. And some of the curves, some of the tropical curves in Rn are what we call realizable. That means that we have like classical curves and a map that tropicalize in a tropical variety. Not all the curves are realizable, but all the curves in R2 are realizable. This is the first example of a non-realizable curve. It is an example of Mikelkin around 8 or 7, I don't know. And the idea is the following one. I take the genus 1 cubic in a plane, and then I choose 3 points, and in each 3 points I take 2 rays that go away from the plane. It means that it's a cubic of genus 1, and if I choose in a generic way my 3 points, it will not be contained in a tropical plane, then cannot be realized as the tropicalization as a cubic of genus 1, because it must be contained in a plane. This is the first example of a non-realizable. Okay, then we can ask again, the maximum genus of realizable tropical curves of degree d in R2. As I told you before, for dimension 2, all the curves are realizable. Then we have that these 3 numbers are the same. If I change the 2 for a generic n, we have these relations. This is the complex bound. This will be greater or equal to that one, because in tropicalization the degree can only decrease. And since the set of realizable tropical curves is a subset of this one, we have also that. Then our work was to study, if I can say something about these 2 numbers. This number is algebraic geometry, and this number depends on the combinatorial. First question: is this number finite? Or we can construct, if I fix n, I can construct something with super. And this is a theorem for Tony Yu in 2014, and he proved that this number is always finite. But he made like a super huge bound. And it's a very. And we have other question, other natural question. If I forget the n, if I take the maximum of the supreme from n, is this number finite? For example, any cubic, I don't care in which dimension it lives, it will never have genus greater than 1. And the third result we found is that this number is not finite. In other words, if I fix a degree greater or equal to 2, and an integer g positive, I can find an n is the dimension, and a tropical curve C in Rn of degree d, which genus is greater than no g. Then, if I don't care about the dimension, I can construct a tropical cubic with genus as big as I want. Moreover, our construction, this curve that we construct, is always planar. What it means that it's contained in a tropical two-dimensional plane. So that means that in R2 we have this equality of the bounds, but if I change my tropical plane to be embedded in a bigger dimensional space, the bound is not the same. And this is because tropical linear spaces are very complicated. For example, tropical lines. This is the only possible tropical line in R1. In R2 we have 2 different combinatoric types of lines. And already in R3 we have 4 different types of lines. For example, for planes, that we're going to construct our curve in a plane. Our plane in R2 is only R2, and in R3 I have 3 different images of a plane. We have something that looks like a classical plane, something that has an edge, and 3 semi-planes going out of it. And this one that is the canonical plane in R3, we have 3 rays. I hope you can see my picture. This is in direction minus E1, minus E2, minus E3, and this is in direction 1, 1, 1. And we have the 6 planes defined by a couple of these 2 vectors. For example, this cone is parallel to the plane z equal to 0, and this one is parallel to the plane defined by the equation x equal to y. We have 2 different. And the curve I will construct later will leave one part in this cone and the other part in this one. That's why I wanted to show you this picture. And then we construct, our construction is a planar curve. Planar means it lives in a 2-dimensional tropical plane. It's Rn of degree d, such that its genus, if you remember, this one was the bound for dimension 2 and R2, and we construct something like this, n minus 1 times the bound in the R2. For example, if n is equal to 2, we recover our construction. We prove also that our construction, well, and then as I told you before, we have this bound given by Tony Yu. We have our construction. And the question is, okay, this is bounding from above and this one from below, how far is from one to the other. And for the moment we only have the result for n equal to 3. And for n equal to 3, it means in R3, our construction is asymptotically maximum. It means if we make the go to infinity, the construction, it goes to infinity as the same as our bound. Then I'm going to give an idea of our construction. And the construction is, in a sense, is as in the philosophy of patchworking. We're going to choose a small piece and we're going to copy it as many times as we need. And for d equal to 3, our piece will be this curve. It's dual to this triangulation. We have a weight 3h in this direction and a weight 3h in direction 1, 1. And we have 3 edges in direction 0, minus 1 of weight 1. This is a genus 1 cubic in the plane. And as I told you before, I will copy this curve in a plane in the cone defined by z equal to 0. And I'm going to copy another copy of this curve in the plane in the cone defined by x equal to y. And it happens that these two rays have the same slope, are parallel, and then I can glue them together. I'm sorry for the drop, it was super difficult to make. But this is, in our construction, this is the easiest example. Is a cubic of genus 2 in a plane. Then we have this construction also for higher dimensions, but the whole idea is always the same. I have a small piece, and then once I increase the dimension by 1, I can put another copy of it. I increase the dimension for once, I can put another copy of it. Then each one for each step, I can add the same number of genus. That's what it was n minus 1, the genus, because I was in dimension 2, I claim one step, I can put another one. And then it means that for the combinatorics, we can construct a cubic, a tropical cubic, obviously non-realizable, of genus as big as we want. It's not bound. If we don't care about the dimension we need, we can construct this curve.
This is not realizable.
No. No, what we want is to see. For realizable curves. In fact, I didn't say it. When we start to studying this, we were trying to understand that one. See if we can arrive to equality here. We were studying equality here. If for any d we can have as many genus as we want. But I didn't say it before. This part, the realizable, is super difficult because we don't have very good system to see if a curve is realizable or not. Then we try, and then we say maybe this one is smaller than this one, and we can prove that way that this one is smaller than that. That's what we start, and we found that it's not the case at all. The combinatorics, for n equal to 2 you have equality, what is surprising now, and just for n bigger than 2, the combinatorics doesn't respect the bounds, the classical bounds. And as I told you before, we have this same construction. It doesn't depend on the curve. We can have a higher dimensional things with what needs happen exactly the same, or almost exactly the same. And we're trying to see if our construction is also asymptotically maximal in higher dimension and in higher dimension in the space and the dimension in the tropical variety. And this was a very short talk, I'm sorry. Thank you very much.
Questions?
So do you have an idea of what happened in higher dimensions? Say for a tropical surface.
I mean, we have a construction. We know that it happened almost the same thing. You can copy it, and then you can again have a genus as overman, or as bigger as you want, or genus, or what you want to call it. But we don't know if it is asymptotically optimal or not. This is what we need to prove now. If it's our construction is for the case. The only case we prove it is for n equal to 3, and it is. It is asymptotically maximal.
Probably I formulated the question wrong. So suppose you have a surface which is embeddable with a minimal embedding in the algebraic geometry case. So is it the case that the invariants in the tropical side are smaller than or equal than in the algebraic case?
I don't know. I think I don't know. Maybe we can recite the question later.
Go back to the previous slide. I'm not happy about this thing. So, I mean, for instance, my plane cubics, my plane quintics can be arbitrarily large genus. What is
If you don't care about it,
I think you'd have to modify the definition of the degree. I mean, passing through this vertex.
For example,
Yeah, you have to do something. I mean, this is just, it's not right.
For example, the first thing we were surprised is that, in general, one theorem that is in the very first day of your tropical course, you will find the Besut theorem course. And for example, here, if I take a point here and a point here, and I take the tropical line joining them, you're going to have many points of intersection.
Yeah, so this is the wrong degree.
Yeah,
We'll have to modify it.
no, but the thing is that the intersection here will be negative. I mean, what is what is your definition of degree?
Well,
I mean, I have.
you have to come up with
I make my picture. I have an edge on direction 111 with weight 3. I forgot 3. I have 3 lines in direction 0, 0, -1 with weight 1. I have 3 lines with direction 0, -1, 0.
No, but in some sense, your definition only deals in intersection with this hyperplanes, coordinate hyperplanes, right? So if it's intersection with this infinite hyperplanes or whatever is 3, then you say your degree is 3, right? But if you sort of modify a little bit, so that should be an intersection with any hyperplane should first have a degree 3. Then I don't think you have this phenomenon.
Which hyperplane? I mean, if
Anyone.
I take a hyperplane here, you have only these 3 intersections.
Or maybe you will.
Okay. I'm glad you're not happy. That's why we can talk about it. Okay. Any other question?
Yeah, is there a tropical analog of Castanova curves?
I mean, that's the idea too. I mean, that's the idea too. I mean, but the analog will be maybe with realizable curves. If we see that's what the origin of the problem. If to see if we can achieve the Castanova bounds always or not. And if we forget about combinatorics, if we forget about.
Don't you have to avoid to ignore the plane curves?
Sorry.
So if you want to somehow match the Castanova bound, don't you have to avoid the nodal curves? So you have to ask yourself about the cubics what's the maximal genus of a cubit which is not
Not plane.
containing it, for instance?
Yeah. But for example, if we can, I didn't think in exactly your example, but as an example of Mikkelkin, he escaped from the plane, like only adding just some edges. Maybe we can make something like this. I don't know. But I agree that